All right, moving into part 3 of section 2, still looking at these parametric functions and how we can use them with calculus. So the last little thing we want to talk about here is we can actually use parametric functions to find the length of a curve. So this is the length of a parametrically defined curve. Let's say we had some function, some parametric function, x is f of t, y is g of t, on some interval. Okay. This could just be some curve out in space here. Let me pull up the book again. Just so you can see the picture. It's something like this, right? We have this curve going through space. So what we're going to do with this curve is we're going to do the same thing that we always do. If we're trying to find the length of the curve, we're going to partition this curve. We are not partitioning it along the x-axis like we have done in the past. We are partitioning it along the parameter. The parameter you can think of as like time. So this would be where the particle is after maybe 1 second, after 2 seconds, 3 seconds, 4, and so on and so forth. So we're going to partition the path of the particle in the parameter variable. Okay, so in doing that, right, partitioning, remember that we're defining I as that interval of the parameter. So we're going to partition I between A and B. And we don't have a specific number of partitions, but let's just say A is going to be the first value T0, and then there's another value T1, T2, all the way down, and then we're going to do in partitions, so all the way down to T sub n, where T sub n is at the endpoint B. So we have in partitions. Lowercase n, stupid word, capitalizing everything. Where we do want to define where these partitions are located, so P sub k is going to be the location of each partition, which you can think of as F at T sub k, G at T sub k. Okay, so if we are going to partition our curve and think about each of those partitions as straight lines. So these red lines are going to be the approximations of the length of my curves. We need to define the length of each of these partitions, which we'll call L sub k. And to do that, we're going to use the Pythagorean identity or the distance formula you can think of. So that's going to be, can I do delta? That's the wrong delta. I want this delta. How do I do it? Increment? I've never heard that before. It's okay. So it's going to be delta x sub k squared plus delta y sub k squared. Okay. And we can define those things because we're just looking at the distance between the partition spaces. So this is going to be the square root of delta x sub k is going to be the distance from f t sub k and f t sub k minus 1. And then we're squaring that. Plus the delta y sub k is going to be the distance from g t sub k and g t sub k minus 1. Let's see if this actually works out. Yes, it looks beautiful. Okay, so the distance of the x values of my partitions, the distance of the y values of the partitions, and then they're both squared. We're going to have to do some tricks here, and some tricks we're going to use the mean value theorem. This is something that we talked about in class once. I think when we did the arc length stuff for just regular functions instead of parameter functions, we used mean value theorem. We're using it here as well. I'm just going to kind of shorthand this a little bit. What we're going to do is we're going to let these delta x sub k's, which is this stuff here. I guess I can copy that down, right? So that's f of t sub k minus f of t sub k minus 1. We're going to approximate this using derivatives. So that distance we could approximate as the derivative f at t sub k star, not 8, star. T sub k star is just some point between t sub k and t sub k minus 1. It's a specific point where this derivative ends up being the same thing as the slope between t sub k and t sub k minus 1. We know something like that exists based on the mean value theorem. And then this is going to be multiplied by delta t sub k here. Okay, so delta x sub k we could rewrite in terms of delta t sub k with this special derivative. We're going to do the same thing with delta y sub k. So that I'm going to skip this part here, the middle part. Delta y sub k we're going to write as the same thing, but now it's g prime t sub k. Now this is going to be a double star here, just because it doesn't have to be the same t as before. It might be a different t. Increment t sub k. These stars aren't super important. They're just a way of notating a special point somewhere in the interval t sub k minus 1 and t sub k. This just happens to be a different special point in between these two things where the slope of g matches the slope between t sub k and t sub k minus 1. Okay. All right. So now plugging that in, this means that my L sub k's is still a square root. So now I'm just going to replace each of these parts by this thing. So my delta x sub k squared, I'm going to replace with f prime t sub k star. Oh, I did the 8 again. And then delta t sub k. Okay, plus, same thing for the g's or the y's. So this is going to be g prime of t sub k double star. Times the delta t sub k squared. Squared. Great. So anyway, that's just substituting out this delta x sub k, delta y sub k with what the mean value theorem gave us. And now we're going to take this one step further. So now what we want to do is that, remember, this is just the length between one of my partitions. If I want to find the total length, then I would add up all of my partitions. We're going to go from k equals 1 to the nth partition of L sub k, lowercase k. Okay, so that is just summing up the right-hand side. Same thing, k equals 1 to n of this square root. And then it's just this thing here that we're copying down. So let me just copy it. That looks nice. Okay, good. Okay, and then this is kind of the trick part to it, right? So what we're going to do is it's still the same sum, but we're going to factor some stuff out. Both of these terms have a delta t sub k squared, so I'm going to factor it out of both of these terms, and then because it's squared, I can even take it out of the square root. So now my square root is just going to have the f prime of t sub k. I'm just going to leave it t sub k star for both of these. Know that they should be different, but I'm too lazy. Okay, that thing's squared. Plus the g prime t sub k star squared. Okay, and then we factored out of the square root delta t sub k. And now it's just a single delta t sub k. It's not squared anymore because we took it out of the square root. Okay, now we're going to take the limit as n goes to infinity, just like we always do with these partitions, right? Eventually we're trying to get an integral out of this. An integral is what we get when we take these partitions as n goes to infinity, which makes an infinite number of these infinitesimally small partitions. So we kind of get our final answer here. What we're going to get is that the total distance L is no longer a sum anymore. Now it's an integral. It's going to be an integral from the endpoints of the partition interval, so from A to B. Still have that square root there. If my partitions are going to infinity, which means that my the distance between the partitions get infinitesimally small, then we don't have to subsidize this t sub k stars anymore. Just know that these are just going to be the variables t. So this is going to be the derivative of f at t squared. Plus the derivative, still in the square root, sorry, plus the derivative at g squared. And then we're going to have a dt at the very end. All right, so this is going to be my formula for finding the arc length of a parameterized curve as my parameter goes from A to B. So this is the official definition. This is what you guys are going to want to write down here for the formula of arc length with partitions. You do have to be a little bit careful with partitions, though. So this gives the total length, but you must be careful because this does not work if the path overlaps itself, not parth, path. And what I mean by that is stuff like circles. Like circles can't keep going around itself. it can only transverse the circle once. So you do have to be careful about parameters because parameters can double back on its same path. So just know that this only works if you cycle through the path just one time. We'll do a quick example of this, and then we'll end the video. Okay, so find the length of the circle, a radius r, defined by, and then here's our parameterization, x equals r cosine t, y is going to equal to r sine t, and then my interval is going to be between 0 and 2 pi. All right, so this just defines a circle of radius a where the origin, the center of the circle is at the origin. All right, and then all we do is we use our formula. So just copying the formula down, the total length is going to be the integral. This is going to go from 0 to 2 pi. And then it's going to be the square root of the derivative of f with respect to t squared plus the derivative of g with respect to t squared dt. All right, so just plug in what we have. So our total length is going to equal out to be this integral. So if I plug in f prime, the derivative of x, this is f, right? Don't forget, x gives you f of t, y gives you g of t. So the derivative of f, derivative of r cosine, is going to be negative r sine t. Oh, I forgot my square root, sorry. So square root of negative r sine t squared, okay, plus the derivative of g squared, so the derivative of this is r cosine t, and that's going to be squared as well. Still dt. All right, clean this up a little bit. Still have the integral, still, oh wow, that went really far up. Still going from 0 to 2 pi, now I'm going all the way down. Sorry about that. Still have the square root. All right, when we square that stuff off, the negative sign just disappears because it's squared, so we end up with r squared sine squared t. And then that is going to be plus the other one, r squared cosine squared t. Okay, still dt. Still have the integral from 0. Oh, I think I figured out what's wrong. On my laptop, my page up and page down are right beside my arrow keys. It's ridiculous. Okay, so we're still integrating from 0 to 2 pi. So I hope you can kind of see what's going to happen inside of the square root. If we factor out an r squared from these two terms, I'm going to end up with sine squared plus cosine squared. And sine squared plus cosine squared is just 1. So we just end up with the square root of r squared there in the square root. And that, of course, is just r. So really, we're just integrating from 0 to 2 pi over r dt. Don't forget that we are integrating with respect to t, and r is just a constant. So this is just going to have antiderivative of that constant times t, and then we're going to evaluate this between 0. How do I make that? I did it before, now I don't remember. I think it was here. Yeah, that's good. From 0 to 2 pi. Well, go away. Oh my gosh. There we go. Yeah, so the antiderivative of RT, which we're evaluating from 0 to 2 pi. If I plug 2 pi, remember we're plugging that into the t, that's going to give me 2 pi r. Minus, if I plug 0 into it, I get 0. So we get this, 2 pi r. And, of course, remember, this was a circle of radius r. Of course, the circumference of that circle is 2 pi r, which is the length around the circle. So I know that was kind of a silly example, but just to show you that it really does work, and we really do get the distance around the circle. All right, I got one more video and one more thing that we need to talk about in this section coming up next.